Welcome to the section on tree methods. A very powerful group of algorithms falls under the tree methods title, and we'll be discussing decision trees, random forests, and gradient boosted trees. Now, I can't really do justice to such a wide variety of topics, so I really recommend you read Chapter 8 of An Introduction to Statistical Learning. Okay, let's start off with a thought experiment to give some motivation behind using a decision tree method. Imagine that I play tennis every Saturday, and I always invite a friend to come with me. Sometimes my friend shows up, and sometimes he doesn't. For him, it really depends on a variety of factors, or features, such as the weather outlook, the temperature, the humidity, the wind, etc. And I start keeping track of these features, and whether or not he showed up to play with me. So I end up getting some data that looks like this, and hopefully this sort of structure looks familiar to you by now. I have temperature, which is some categorical column, the outlook, humidity, windy, and then my label, whether or not my friend came out to play with me. I want to use this data to predict whether or not he will show up to play. And an intuitive way to do this is through a decision tree, which we've drawn out here as a little diagram. And in this tree, we have nodes. And nodes are the split for the value of a certain attribute or feature. And you can see here, I'm splitting on the outlook feature, then the humidity feature, as well as the windy feature. The edges are the outcome of a split to the next node. So you can see here, if I split outlook on sunny, then my next node becomes checking for the humidity. And after that, we have two more features, which are the root and the leaves. The root is the node that performs the first split. In this case, that's that outlook node. That's the very first feature that I'm splitting on. Then I have the leaves, which are the terminal nodes that predict the outcome. So those green and red yes or no nodes. Now, a question you may have is, how do we actually decide what features to split on and in what order? So if you go back one slide, how do I decide to split on outlook first instead of humidity first? So what we want to do is try to get some intuition behind these splits. Let's look at this imaginary data set with three features, X, Y, and Z, with two possible classes, Class A or Class B. Now if I split on Y, that gives us a clear separation between classes. All I have to do is ask, does Y equal 1? And then I can split perfectly between Class A and Class B. So if we go back one slide, I can see here that according to that middle Y column, that lines up exactly with the class that I'm trying to predict as far as the split value. So it may be a good idea to try to split on that first. We could have also tried splitting on other features. And we can see here the results of first splitting on X, Y, or Z, where Y gives me that perfect classification if I split on that first. So what we really want to do is figure out some sort of methodology for deciding what features to split on and how to split on them. So entropy and information gain are the mathematical methods of choosing the best split. And I would refer you to the reading assignment if you're interested in finding out more about the mathematics behind entropy and information gain. All of this stuff is done by Spark for you behind the scenes. But if you're interested in the mathematics behind it, you can always refer to that Chapter 8 reading assignment, and that will definitely touch upon entropy and information gain, which is basically how we decide the best split. Now the methods we just discussed refer to decision trees, but we can try to improve performance by incorporating a random forest. What we can do is use many trees with a random sample of features chosen as the split, where a new random sample of features is chosen for every single tree at every single split. And keep in mind, this method works for both classification and regression tasks. Classification will just end up taking votes for what class this particular sample belongs to. Regression will just take the average of the predicted values and then set that as its predicted continuous label. So you may be wondering, what's the point of choosing a random set of samples? That's kind of a weird idea. Well, suppose there's one really strong feature in the data set. Then most of the trees will end up using that feature as the top split, resulting in an ensemble of similar trees that are highly correlated. And then averaging highly correlated quantities does not significantly reduce variance. So what we end up doing is by randomly leaving out candidate features from each split, random forests decorrelate the trees, such that the averaging process can reduce the variance of the resulting model. So finally, let's discuss gradient boosted trees. Gradient boosting involves three main elements: a loss function to be optimized, a weak learner to make predictions, and an additive model to add weak learners to minimize the loss function. So let's discuss each of those. The loss function in basic terms is just a function or equation you will use to determine how far off your predictions are. So for example, we've actually seen some loss functions. The regression may use a squared error loss function, and something like classification may use a logarithmic loss. We won't have to deal with this directly using Spark as far as choosing the loss function. In fact, basically all the theory that we discuss here happens under the hood. In fact, that's kind of the whole purpose of using Spark, is that someone already coded this out for you and took care of all the hard work. So on to that second point of the weak learner. Decision trees are used as the weak learner in gradient boosting. It's common to constrain the weak learners, such as constraining the maximum number of layers, or nodes, or splits, or leaf nodes. Then we have an additive model, where trees can be added in one at a time, and existing trees in the model are not changed. A gradient descent procedure is used to minimize the loss when adding the trees. So what is the most intuitive way to think about all of this if Spark's basically doing all of this for us under the hood? What do you want to keep in the back of your mind when using gradient boosted trees? So here's a nice way to think about it in 3, quote, easy steps. So the first step would be to train a weak model M using data samples drawn according to some sort of weight distribution. So each sample has a weight to it. And then what we want to do is increase the weight of samples that are misclassified by model M, and decrease the weight of samples that are classified correctly by model M. Then we train the next weak model using samples drawn according to the updated weight distribution. And in this way, basically what we're doing is the algorithm always trains models using data samples that are, quote, difficult to learn in previous rounds, which results in an ensemble of models that are really good at learning different parts of that training data. Basically, this is boosting the weights of samples that were difficult to get correct, which is where this boosted name comes from. The real details of gradient boosting lies in the mathematics, which you may or may not be ready for depending on your background. So I encourage you to read the full details. They're towards the end of Chapter 8 in ISLR, in case you're interested in the mathematics behind everything we discussed here. But for the most part, Spark is taking care of all of this for you. Someone already did the hard work of coding all of this out, and then before that, someone did all the hard work of figuring out the mathematics behind all of this. So again, Spark handles all of this for you. You can just use the defaults if you want, or dive into ISLR and begin to play around with some of the parameters. Okay, let's continue on by walking through the documentation example for Python and Spark and these various methods.